We're going to take a few notes today, and then we are going to look at lab stuff also today. So, yeah.
Do we turn our homework in? Yes, we do.
No. You eventually. You will turn it in at the end of the unit. Does that make sense? Yeah. So kind of like we did in accelerated physics, except I'm not going to stamp it in between. Yeah. And like I said, I know that I have access to the all of the solutions, and as soon as I have that, I'll get it, and it'll be before your first test. So yeah. All right. So one of the things that I really liked in the Feynman article, and that we kind of talked about tangentially, it wasn't like our primary goal, was talking about how laws are laws right until they're broken. And the only way that we know that they're broken is if we have good measurement tools, right? And so thinking about that in terms of trying to make measurements and make good measurements that, it's not like you're always trying to break physics, but you want to take accurate measurements to see if physics is breaking, I guess, is one way to look at it. And when you're doing that, it's important to look at error and uncertainty, and that's really what I want to look at today. So hopefully this is not going to be too crazy at me, but we're just going to talk about and I will tell you that this is not content that's covered directly in your textbook, at least not in the way that I'm going to present it to you. The reason I'm telling you that is that when you're working on the homework for today, which is not from your textbook, I don't want you to freak out and be like, where is it? Because it's not really in there. It's just kind of from our conversation. Does that make sense? So when we're talking about error and uncertainty, there are three kind of big types of error that exist. Three categories, I guess. So number one is random error. And these should not be huge surprises in terms of these terms or these ideas. We've talked about this before. But maybe in terms of that bouncy ball lab that we did last time, what's an example of a random error that you might get? Or where might you get a random error? Any ideas?
Didn't bounce as high one time. Or it bounced higher because you threw it up first.
Yeah. So did you guys all catch what she said? Like if you threw it down or threw it up a little bit, then it's going to bounce a different amount at least, right? Yeah, absolutely. That would be a perfect example. That's the kind of like thing that I had in my head. So like you do the experiment 4 times, let's say, and you get 10.3, and then you get 10.5, and then you get 11.9, and then you get 10.2, right? Mm-hmm. So that 11 point whatever I just said, 9, thank you, probably not the same, right? That's probably one where we made a mistake. So those random errors are things that you can notice, and you'll notice probably right away because the values are fluctuating, right? So they're pretty easy to identify. How can you avoid them or try and minimize the effect of random errors in experimental physics? More trials, right? The more if you only did it one time and you got the 11.9, well, that's a sad thing because that one was not correct, right? That was a bad answer, and that's the only one you did. But if you do it 7 times, and you get that 10 point something most of those times, and maybe an 11 or a 3 one of those times, then you know that those ones are are not accurate. So yeah, so we're going to say we can minimize through multiple trials. Absolutely. And not only are you going to do multiple trials, but then when you are looking at your data, are you going to use every single one of those trials, or what are you going to do with that data? What's that? Average it, yeah. So we're going to minimize through multiple trials and an average. And I think I probably told you guys this before, but if you can't read something that I write up here, please let me know. Sometimes my handwriting gets a little bit bad, especially at the end of the day. All right, this should not be surprises, right? This stuff makes good sense. Okay, so that's error possibility number 1. Error possibility number 2 could also happen to you. Systematic error. systematic error before? What is systematic error? Again, you can talk about it in terms of the bouncy ball lab, or something else too.
Would it be like something wrong with how you designed your experiment?
Yeah, so you're like carrying it out incorrectly or something. Yeah, Daniel, what else?
Like you're holding the ruler at an angle.
Right. And are you holding the ruler at an angle one time? The whole time, right? So yeah, you've got it. So you're doing the same thing wrong every single time. So your data is going to be really consistent, but it's going to be consistently wrong, which is, I mean, it's nice that it's precise, but it's not at all accurate, right? So for a systematic error, that means that there's something wrong with the design, or the implementation, or maybe both. We don't know. And as Daniel said, there might also be some sort of like misuse of equipment, right? Like you're not using your equipment properly. Absolutely, absolutely. Now, is it easy to identify systematic errors? Like, do you know when you're doing the lab that you're doing something wrong? Sometimes. If you do know that you're doing something wrong, then maybe you should fix it, right? Yeah, so, I mean, the idea with the systematic error is that you should be trying to be a good kid, trying to be a good experimentalist, and do things consistently, and da-da-da-da. So we're trying to minimize them, but they might be hard to see, just if you're looking, you're looking at your list of data. One way that you can see systematic errors really nicely, though, is when you look at averages, or more specifically, oh, you really cannot see that color, can you? Sorry. When you look at like a graph. So if in this lab that you guys did last time, I think we all graphed. I don't know, I haven't looked carefully at all your graphs, but I think a lot of people put bounce height over here and drop height over here. Can I do that? Is that okay with everybody? So not saying you had to, but I'm just going to say, let's pretend that we did. So here's bounce height. Oops, that's supposed to be a C. And this is drop. I'm not saying you had to. I'm just saying one might. And if you did, that's lovely. And most of you, I think, when you graph this stuff, what did you find when you graphed those points? Sort of made a line? Something like that? So if you did things all perfectly well, yeah, they might have made a line. Now, you could have made a line with some pretty hefty systematic error, though, if you got data that went like this. How would that imply to me that there's systematic error? What's wrong with that picture?
If you dropped it from 0, then it's
yeah, take them. Say that again.
If you dropped it from 0, it pops up way higher than.
Right. Do you guys see this? If you extrapolate that back, then if you drop it from a height of 0, it bounces to a height of something that's not 0, right? So does that mean that the slope is wrong? It probably means that you were holding the meter stick wrong or something, right? So that this all needs to be shifted down a little bit. So this is one of those good opportunities to see a systematic error. If you get a graph that looks like it's the right shape, but there's something wrong, okay? You can know often, though, like what direction, like, oh, obviously I'm measuring this to be much higher than it actually should have been. Okay, so maybe it was because you were reading from above or something like that, but yeah. Is this making sense? We're still happy? Awesome. All right, so that's 2 down, 1 to go. So random error we can pretty effectively minimize if we're careful, right? And if we're aware. And if we get one piece of data that's really, really weird compared to the rest, get it out of there, okay? Systematic error, we don't necessarily know that it's happening, but we can try and minimize it by making designs carefully. We can implement things carefully. We can make sure that we know how to use the equipment that we're using, okay? And we can look at our data and make sure that we're set. The third kind of error for better or worse, is inherent. You're stuck with it. You will always have it. Which is kind of depressing, but it's true, okay? It's called, I guess it's kind of like admit failure to start. Like, maybe I shouldn't even do the law. I was going to have error in it. No. It's reading error. And reading error is the error that you have because of the measuring tool that you're using. Okay? Every measurement tool is flawed. Okay? Every measurement tool is flawed. So are you looking at that awesome ruler? It's not flawed. That one is perfect. Yeah. And most of you have heard this spiel from me before. We talked about this maybe like the first day of accelerated physics too. Okay? Is this a measurement tool? Yeah, it's a meter stick, right? It's a stick that's a meter long. Can I use it to measure stuff? Sure. Will everything be perfectly accurate always? No, because when I put it up here like this, I'm like, oh, well, it's not quite a meter. Good for me, right? Yes! And then, Rachel's like, okay. Rachel's like, well, I've got this meter stick. It's better. Why is this meter stick better? It's a little more specific, right? It's got these little divisions. So I can be a little bit better. So I can measure a little bit more accurately. Okay, well, there we go. But is it perfect? No. So then Caleb's like, oh, well, I can get you better on that. I get you this meter stick right here, right? That's kind of how you would say it too, isn't it?
Probably.
Yeah, I knew it. Right? It has 100 little divisions on it. That's a lot of divisions. That's a lot of divisions. Right? And so I can measure this table now. Woo! And I know much more accurately. But is it perfect?
Yes.
He's like, it's perfect! But then he's like, whatever, not best do again. Ha! Another factor of 10, yes?
Yeah.
It's perfect, right?
No.
Why not? Look at all those little tiny lines. How is it not perfect?
It can be tinier.
Yeah.
They could be tinier, right?
Yes.
Even more, and even more, and even more. And can we get to the perfect measuring tool?
Maybe not.
It's not possible. It's not possible to get to the perfect measuring tool. So we have to acknowledge the fact that it's not perfect. And it never will be. Because there's always something that you can do more accurately, right? You can get a better measuring tool. So that doesn't mean that we just quit and go home. Say, oh, I guess I don't have the best measuring tool ever, so I'm done. It just means that we have to acknowledge it, okay? And it's actually kind of to our advantage. Let me show you why I say that. Let's say that when I was taking this data, some of the data wasn't actually where it is. It was like more like, oh hush. It was more like up here, and then there was another one that was like down here. So they weren't really quite linear. Do you see what I'm saying? Okay? Now, if I just try and draw a line, it's not going to work so hot. But if I'm able to give this some error bars, then they all still fit. You see kind of what I mean? Okay? And as long as my error bars all still fit within my line, then I'm okay. It's all good. So I'm like, I can only be so good. But it works. It works. Give me a break. That's what we're kind of saying. All right. So reading error is inherent in a measuring tool. It's going to be there. We just have to acknowledge the fact that it's there. It cannot be improved. By multiple trials. It just is. It just is. Okay? And because it just is, and because we have to admit that it's there, we must record the measuring error. Or the reading error, excuse me. every time from now on, when you do a lab and you're making a measurement, you also need to record this because now we have to admit it, right? Which is actually good, again, because if you don't admit it, then I should expect your data to be perfect every single moment of every single day. And while Jack's certainly will be perfect every single moment of every single day, right?
Probably.
Right. Not all of us can quite live up to that standard.
I try really hard.
You do try really hard. You do so many multiple trials that no.
My measurements
It's just whoa.
on point.
We do need to write down our reading error amounts, okay? It differs between analog and digital measuring devices. Have you heard about analog, the word analog, the word digital? Analog clock, digital clock, ding! What's that?
Analog.
What's this?
Digital.
Yeah. Okay, what's the difference?
Digital has like the actual like I don't know, digital like just it doesn't have like the
actual numbers.
hands. It has just like numbers.
It has numbers, right? Yeah, absolutely. What's the, okay, so one has numbers, one doesn't. Tell me more.
Because you could say you're more specific with analog
What do you say?
because you have the seconds, the minute, and the hour hand. The digital doesn't have the seconds unless I guess you would.
Some digital does, right?
Yeah.
But even if, okay, so let's say, for sake of argument, just so that we don't have to talk about how hard it would be to read or not read, let's say that we have a digital clock with no seconds. We also have an analog clock with no seconds, no seconds hand. Does that make sense? Okay, those are the two situations that you have. Which one is going to be more accurate to read?
Digital.
Analog.
Digital, analog. Raise your hand if you think it's digital. Raise your hand if you think it's analog. Raise your hand if you don't have any idea. Okay, why do you have any ideas? Oh wait. What's? If you were gonna lean one way, which way would you lean? What's your gut? Why is your gut telling you that?
I don't know, because you can see, like, even without the seconds, you can still see, like, when the hours and the minutes move.
Say that loud.
Even without the seconds, you can still see, like, the hours and the minutes move.
Exactly. That's the key. That's the reason that analog is more accurate, because you can tell if it's halfway to another minute. Do you see what I'm saying?
Okay.
You can tell if it's really close to the next minute and it's about to switch over, whereas if you're looking at a clock, a digital clock, right? Like if I'm trying to time something with a digital clock, and I like look at my clock and I'm like, oh, it's 1:50, and then, and it's like a minute and a half long thing. I don't have any idea if it took 3 minutes or if it took, you know what I mean? Because you don't know when it's going to switch over. So yeah, with an analog measuring tool, you can be more accurate because you can tell how close it is. Is it halfway there? Or is it only just starting there? You guys, this making sense? Okay? Yeah. So with an analog device, so those are ones with a continuous readout. Okay? With a continuous readout, you can tell halfway, part of the way, whatever, something like that. And so therefore, the reading error is 1/2 of the smallest division. Okay? What does that mean? I can totally read your face. Let me tell you what that means. Is this thing analog or digital? Analog. It's kind of weird to call it like a meter stick. Like, what is that? It is. It's analog. It doesn't have a printout, right? So if I'm going to measure the height of this table, Rachel, how tall is this table given this meter stick? Is it a meter or it's not? It's not. So it's like 0 or it's like closer to 1? Closer to 1. So she's going to say it's closer to 1. So it's like 1 meter. Plus or minus a half meter. Does that make sense? We're halfway there, right? If it was like down here, you would have called it 0. If it's up here, you're going to call it 1. Okay? Now, if... Elena gets this one. Nah, we'll go this way. And you were going to measure, here, we'll measure the table. Can you see it over there? How tall is it? So go there-ish. So almost 8 decimeters, or 0.8 meters. So that's like 0.8 meters plus or minus 0.05 meters. Does that make sense? Because it's plus or minus that like 10 centimeters. Is that okay? Or like half of that? And then you can keep going and keep going and keep going. Does that make a little more sense? So that's what the half of the smallest division thing is. If it's the smallest division is a meter, then it's a half a meter, etc. So, go ahead. So like, I don't know if you remember when you were in accelerated physics, and I always find this funny, and I don't know why I keep it on the questions, but there's always a question on some of the labs that say, how many sig figs did you get and why? And inevitably, I have students that will say, we got 3 significant figures because that's what my group decided on. You don't get to just pick, right? The answer is really because of how good your measuring tool is. Does that make sense? Now, that means that when you were doing your bouncy ball lab, you should have been able to measure to the millimeter, plus or minus half a millimeter. Were you able to do that with the bouncing? I'm going to go with no on that. Unless you're like bionic and awesome like that. Whoa, you are all awesome, but maybe not in that way. Okay? So there is, and I'm going to tell you the digital thing in just a minute, but I do want to say that I put in kind of a caveat for taking into account human reading error. Okay? So I'm going to say that you may account for human reading error. So in the lab that we did so maybe with the drop height you were sure to a centimeter, okay? But with that bounce height, maybe you're sure to within like 3 centimeters or 5 centimeters or something like that. That's reasonable. And if you said that you were sure within a half of a millimeter, then that would mean that every single one of these dots should be right on the line. No fluctuation at all. No excuses. Right? It's not that easy to read it. Okay, that's what I'm talking about. One more little thing about the digital stuff. Because I haven't told you how to measure digital yet, or how to account for digital readings. With the digital, can you tell how close it is to the half? No. So the reason that digital is less accurate is because it's only going to be, the plus or minus is the smallest division. Okay. So if I'm reading a stopwatch that doesn't have seconds on it, and it says 0. Or that's hours, and then or the minutes and then the seconds. If it said 35 seconds, then I don't know if it's almost 36 or if it just turned 35, right? So it's going to be plus or minus 1 second. Does that make sense? Okay. Is this sitting okay with everybody? So we're going to use this in our next lab. We're going to try it out. We're going to see how that all works. Life is good? Okay. I'm going to pause.